Welcome back to our heat transfer class, where we're delving deeper into the one-dimensional, steady-state heat conduction. This video was made with the support of InnoEnergy. The topic of one-dimensional steady-state conduction is divided in several lessons. There is at least one video for each lesson. Let's continue with the third one. This lesson is divided into several parts. Let's start by defining what the criteria are for calculating insulators. We call insulation the layers of low thermal conductivity material that we install to reduce heat transfer between two systems. For example, a layer of insulating material to reduce heat losses from a building to the outside environment. Let us start by analyzing a wall, for example, made of brick, that we want to insulate with an insulating material. The analysis will depart from the calculation of heat losses through the wall. Inside, the brick wall is in contact with air. As the interior walls can be assumed to be at similar temperatures, it is not necessary to consider the radiation between them. Thus, inside the wall, we will have convection with the indoor air and we can apply Newton's law. On brick and insulating walls, we apply Fourier's law. The heat flux that reaches the surface of the wall by conduction is equal to the heat flux by convection with the outside air, plus the heat flux by radiation with the outer surroundings. Recall that for calculating composite walls, we can use the electrical analogy, and that the resistance for radiation depends on the surface temperature. Therefore, it is not practical for simplifying calculations. We can use this circuit for writing the heat transfer rate equations in this composite wall. Heat losses throughout the wall can be written as the difference of temperatures divided by the sum of three specific thermal resistances. The heat that arrives by conduction to the outer surface is equal to the sum of the heat transfer rate by convection plus that of radiation. The heat balance in the outer surface can also be written as the combination of the above equations. For all types of walls, the thermal resistance of the insulation depends on its thickness. For radial systems, like cylindrical and spherical walls, the outer area depends on the insulator thickness. If the thickness of the insulation is known or zero, these equations allow to calculate the outer surface temperature and the heat losses. Calculating first the outer surface temperature, and after that, the heat transfer rate. If the thickness of the insulation is unknown, then we have two equations and three unknowns which are marked in yellow in the equations. We must impose one of them as a design parameter. If heat losses are prescribed, we can calculate the surface temperature and the thickness of insulation needed. Prescribing a maximum allowable value for heat losses is related with the operational costs. The goal is to reduce heat losses and energy costs. If the surface temperature is prescribed, we can calculate the thickness of insulation needed and heat losses. Prescribing a maximum allowable surface temperature is related with safety regulations, mainly for hot surfaces. Let's study how heat losses and surface temperature change with the insulator thickness. We must take into account that the insulator cannot be infinite, nor can we pretend to have zero losses. First, because it is physically impossible. Second, because the insulation has a cost. Using the heat transfer equations for composite walls, we can calculate the minimum insulator thickness that fulfills one of these conditions or both conditions at the same time. Plane walls. In plane walls, we can do the calculations using the heat flux, Q divided by A. After calculating the heat flux, to calculate the heat output, it will be enough to multiply by the surface. We can use this circuit for writing the heat flux equations in this composite wall. The equations for the balance between the inner fluid and the outer surface, for the calculation of outer convection and radiation, and for the energy balance in the outer surface are simplified for plain walls. If the heat flux is prescribed, we can calculate the surface temperature and the thickness of insulation needed. If the surface temperature is prescribed, we can calculate the heat flux and the thickness of insulation needed. Let's use these equations to calculate an example. Berta and Albert live in a single-family home in northern Catalonia, where winters are cold. Their energy bill is continuously rising. Insulating the house walls could be a solution. However, they don't know how to calculate the insulation needed. Can you help them? Let us start by analyzing walls, which are made of brick, before installing the insulation. The brick thickness is 9 mm, its thermal conductivity is 1 and its emissivity is 0.93. We can assume that both the outer air and the surroundings are at ambient temperature. Berta and Albert want to keep home at 24 Celsius degrees. After consulting weather statistics, we check that the average ambient temperature in December is 9 degrees. We must assume an average value of the inner convection coefficient, also an average value for the outer convection coefficient. Making the energy balance in the outer surface per unit of area, we can calculate T2, the outer surface of the wall, before installing the insulation. The heat flux in these conditions is 92 watts per square meter. Now, we need to know the total surface and the price of energy. Berta and Albert gave us an approximate surface of 90 square meters. Also, the price of natural gas for the tariff TUR. In December, the space heating system is running 24 hours per day, 7 days per week. The energy consumed by Berta and Albert in December is around 6,157 kilowatts-hour. So, they are paying around €374 only for the gas consumed before taxes. Let us help them to reduce the energy consumed for space heating in December by 85%. The objective is to reduce the heat flux below 13.79 watts per square meter. We will use glass wool panels with a thermal conductivity of 0.035. We will start calculating the minimum insulator thickness that fulfills the objective. The first step is calculating the outer surface temperature for the maximum allowable heat flux. After calculating the surface temperature, using the heat balance in the outer surface, we can calculate the minimum insulator thickness to fulfill the objective of heat flux reduction. After consulting catalogs, we decided to install standard 40 mm insulating panels. Now, it is time to calculate the heat losses for the selected standard thickness of insulation. We must start calculating the surface temperature because it will be different than the value calculated previously. For this configuration and specific boundary conditions, the heat flux is reduced to 11.48 watts per square meter. Now, we can calculate the new expenses for natural gas supply in December. Savings for the month of December can be estimated in around €327. After consulting some companies, we get a quotation of around €2,100, all costs and taxes included. For calculating the time of investment return, you need to do the calculations for the average conditions from January to December. All in all, it is a good investment improving the insulation of Berta's and Albert's house.